Hi, let's talk about Merkle-Damgård. So the scenario that we have is we have a hash function for messages of length L of n with a hash length of n, and we essentially want to have a hash function for arbitrary length messages. And we basically do this in two steps. The first step is to pad this message into a longer message that has exactly multiple of L of n bits. This because this is a fixed length hash function, so we need like 2 L of n bits input, and we can only get that if our message, the original one, is a multiple of L of n. So the way it's done in Merkle-Damgård is we add zeros to the end of x, so that its length becomes a multiple of L of n, and then we add one additional block that encodes the length of the original bit string. This because if, for example, your string is 0, 0 that you want to hash, then the padded version of that would contain a bunch of other zeros appended to this. And if we didn't add the length to all of this, then we wouldn't be able to distinguish whether this padded string happened to be the result of padding x or happened to be the result of padding x prime that has like 3 zeros, for example. Okay, because they all will be padded to the same string here. So to alleviate this, we add one more block, and in this block we just write how many bits the original string had. Then essentially we know how many bits we would have to, like in our minds, remove in order to get the unpadded string, and then like this ambiguity here is not there anymore. So that's what's happening in the first two steps, and then in the other steps we do this hash chain. So we always hash the previous block hash and the next block. And for the first block, we just say we hash just zeros together with the first block. But then for the second block, we take the output of that hash it together with the next block. Then after we've added all of the blocks into this, we get the output, which is the output of the last hash function in this chain. So to get an intuition for this, let's say we have actually an adversary that gave us a collision for this construction. Meaning that he gave us x's and x primes, so that the output of the two hashes is the same. And now what we can do is essentially we can go back in this chain and look for the first hash where a collision happens. So we would start at the end. We know that the output of these two hash functions is the same. So also this last hash value is the same. Now we have essentially two cases. Either the input to those two hash functions is also the same, then, well, no hash collision happens, this is fine. If the input to those two hash functions is not the same, but the output was the same, then we have found our hash collision. But if this was not the case, so if we didn't find a hash collision at this position here, then we at least know that the input of both of these in the chain was the same. So then we can go one step back, take a look at this hash function here, and at its input, and we know that at this part, we again have the situation that both of these hashes have the same output. We just need to look at the input and kind of hope that there's a collision there. So through this, we may go back several steps, and then let's say we finally arrive here. We still have that these chain values are the same because we didn't find a collision before this. And then we notice that actually this input here is not the same. And then we will have found our collision. And now my question to you is, do you have a precise argument why there needs to be such a position where the outputs of the hash functions is equal, but the input of the hash function is not equal? Think about it for a second. Okay, so the argument is, if all of these inputs to all of these hash functions would always be the same, then this is not a hash collision, because then in particular, all of these xi are the same. So the input to this hash function just was the same. And then obviously this is not a collision. So because one of the xi is not equal to the xi, its corresponding xi prime, somewhere in this chain there needs to be this deviation for the input. So what happens if the length of these two chains is not the same? So let's say the message X is way longer, it has very many blocks, and the message X prime is pretty short. So in this process of going through the hashes, we would eventually pretty quickly find this zero origin hash for one of these chains, and the other one is still going. How do we fix this situation? So how can we still argue something about this then? Okay, the answer to this is if these two chains have different lengths, then also x and x prime have very different lengths. And in particular, this will mean that xb plus 1 and x prime b plus 1, which were the lengths encoded, they will be different. So in this case, if the two strings don't have the same length, or the two chains don't have the same length, we will get our collision already here in the first try. All right, the last thing I want to talk about is what actually happens if our hash input, the x, if it's like really, really long, if it has a length more than 2 to the L of n. Because in this construction here, we had to assume that the length of x is at most 2 to the L of n, because otherwise we wouldn't be able to encode the length of x into this one block. So this one block has length L of n, so the largest number we can encode into this is 2 to the L of n minus 1. However, what we wanted was this Merkle-Damgård construction. We did all of this with the express intent of saying, okay, now we finally have a collision with a hash function for arbitrary length messages. But it seems like it's not arbitrary length, right? So it's almost arbitrary length. It's really long length, but it's not arbitrary length. So my question is, how do we remedy this? So how can we handle this? What do we set this hash value to? We can't really do the same trick of encoding the length into the last block. All right, so the nice thing about this question is that there are essentially no wrong answers, because in the collision finding game, like no adversary will ever be able to input something that is longer than 2 to the L of n. Because 2 to the L of n is super polynomial, and just writing down a super polynomial length string is not possible for a polynomial time algorithm. So in particular, he will never be able to output a hash collision that will involve one of those values that are really long. So the easiest way to fix this, I think, is just to set hs of x to 0 for all of the x's that are really long. And this means now that we have this giant pool of collisions that we have introduced now. So for every x that is really long, the hash value of that really long x is just 0. So all of these x's collide. However, because, again, it's hard to write down these long x's, an adversary will never be able to claim this as a collision. And by the way, we had the same problem when we did this Mac extension, where we had this kind of block mode in order to sign multiple blocks with the same Mac. And there also one of the components that we put into the Mac was the length of the message. There we had the same problem, that as soon as the messages that we wanted to Mac become too long, then this Mac wasn't well defined anymore. But there also the same solution kind of applies. We can just say, okay, verification for really long messages just accepts. And then we still have that this Mac would be correct. But that's just kind of a formal thing that we need to think about if we really want to have like arbitrary length stuff. We can just make sure that everything is still like correct. So this is still like a valid hash value that is output then, or this one would still be a valid Mac that is output in this case. And we can just forget about security for those values because they will never be output by any PPT. Okay, that's it for Merkle-Damgård. Thanks.